In this video, we will talk about the determinant of a 3x3 matrix. Let's start with the Sarrus rule. And this rule says that if you have a matrix like this, A, then to compute the determinant of A, essentially what we need to do is we need to repeat the column, the first column here, and then we do A, D, F, and then we repeat the column, the second column, B, E, H, and then this determinant is going to be the product of this diagonal that starts here, A times E times K, plus the product of this diagonal, B times G times F, plus the product of this diagonal, C times D times H, minus, now we go in this direction, the product of this diagonal, C times E times F, minus the product of this diagonal, A times G times H, minus the product of this diagonal, B times D times K. Let's do an example. Let's suppose that we have A equal to then in order to compute the determinant of A, what we do is we repeat the first column, 1, 3, 2, and the second column, negative 2, 4, 0, and then we multiply. 1 times 4 times 4 is 16, plus negative 2 times negative 2 is 4 times 2 is 8, plus 3 times 3 times 0 is 0, minus, now we start here in this diagonal, 3 times 4 times 2 is 12, 24, minus 1 times negative 2 times 0, which is 0, minus negative 2 times 3 is 6, times 4 is negative 24. This is 16 plus 8, 24, minus 24 plus 24. Then this determinant is equal to 24. Let's see another way to compute the determinant of the same matrix. And we're going to talk about something that is called the Laplace expansion. And let's suppose that we have the same matrix, A, but now in order to do the Laplace expansion, we need to pick either a row or a column. Either one will work, or either any row or any column will do the job. Let's pick the first column. Then what we do is that each entry is going to have a sign assigned to it. And in order to decide about that, this one has a positive, the other one a negative, a positive, negative, positive, negative, positive, negative, positive. Then what we do is we multiply the number that is in this. We're going to select row 1. Let's select row 1. Then the determinant of A is going to be equal to positive, right? Because we are selecting this. This one is positive, and then 1, because we have the 1. And then when we think about this entry, and if we remove this column and this row, we end up with this matrix, which is the matrix 4, negative 2, 0, 4, right? Then we do the determinant of that matrix. This means the determinant of that matrix. And then we continue. Then the next thing is a minus, because here we have a minus, and then the value of the entry, which is negative 2, times the determinant of this matrix that we get by eliminating, we are considering this entry, then we eliminate this column and this row, and we get the matrix 3, negative 2, 2, 4. 3, negative 2, 2, 4. And then plus the value of that entry, 3, and then times the determinant of the matrix that we get when we remove this column and this row, 3, 4, 2, 0. 3, 4, 2, 0. Okay, then what is this? This is 1 times 16 minus 0 plus 2 times, and this is 12 minus negative 2, it will be plus 4, and then plus 3 times 0 minus 8. What is this? This is 16 plus, this is 16 times 2, 32, and this is 3 times negative 8 minus 24, and we get the same number. Notice that when we do the Laplace expansion, we can select any row or any column. What happens if we select row number 2? If we select row number 2, then the determinant of A, we're going to select this row. Then we look at this entry. Then this entry goes with a negative. Then it's negative, the value of the entry, which is a 3, and then we have to remove this column and this row, and we end up with the matrix negative 2, 3, 0, 4, and then we do a plus because we go with this entry, the value of the entry, which is 4, and then the determinant that we get when we remove this row, this column and this row, which is 1, 3, 2, 4. 1, 3, 2, 4. And then this entry goes with a negative, and then the value of the entry, which is negative 2, times what happens when I remove this column and this row. I get the matrix 1, negative 2, 2, 0. 1, negative 2, 2, 0. Let's do this. Here we have negative 3 times. This determinant is negative 8 minus 0 plus 4 times this determinant, which is 4 minus 6 plus 2 times this determinant, which is 0 minus negative 4. And then we end up with negative 3 times negative 8 is positive 24 plus, minus, because here we have negative 2 times 4 is minus 8. And then here is, this is 4 times 2 is plus 8, which is equal to, again, 24. Let's see what happens if we pick the third column. Then let's say column 3. Then the determinant of A is going to be equal to, we're going to select the third column. Then this entry goes with a plus, and we do plus 3 times, and then this determinant, which is 3 of this matrix, 3, 4, 2, 0. 3, 4, 2, 0, and then a minus, and then the value of the entry, which is negative 2, and then times, and I remove this row and this column, I get 1, negative 2, 2, 0. 1, negative 2, 2, 0, and then finally plus 4 times is positive, then the entry, value of the entry is positive, the value of the entry is 4 times the determinant of 1, negative 2, 3, 4. Then let's do the computation. This is 3 times 0 is 0 minus 8, 3 times negative 8, plus 2 times, this determinant is 0 minus negative 4, it will be 4, plus 4 times 4 minus negative 6 is 10, and then we have negative 24 plus 8 plus 40. And this is equal to 48 minus 24. Once again, we get the same value. Remember, these are examples of computing the determinant using Laplace expansion. Let's see a third way to compute the determinant of this matrix. Before doing that, I want to explain some matrices which are very easy to compute their determinant. And let me talk about a matrix that is upper diagonal. When we have a matrix, these entries here, this is called the main diagonal, the diagonal. Then upper diagonal means that under the main diagonal, you have zeros. Then here you can have any number, and any number, right? Then essentially you have a matrix of this type. Let me write it better like this. A, B, C. This must be 0, D, E, 0, 0, F. This is a matrix that is called upper diagonal. And for this matrix, if this is our matrix A, the determinant of A is just the product of the elements in the main diagonal. It's A times D times F. What is a lower diagonal matrix? A lower diagonal matrix is a matrix that looks like this. A, 0, 0, B, C, 0, D, E, F. Above the diagonal is 0. That's the reason it's called lower diagonal. And again, the determinant, if this is my matrix A, then the determinant of this matrix is just the product of the elements in the diagonal. Determinant of this matrix. Finally, what is a matrix that is diagonal? A diagonal matrix. A diagonal matrix is a matrix that looks like A, 0, 0, 0, B, 0, 0, 0, C. Below the lower diagonal is 0. Above the diagonal is 0. Only the entries that may be different from 0 are the entries in the diagonal. They could be also 0. But then the requirement is that these 3 numbers are 0 and these 3 numbers are 0. And the determinant of this matrix is just A, B, and C. Then let me do some examples. If you have A equal to 0, 4, 0, negative 1, 7, 0, 0, 3, then the determinant of this matrix, since this is upper diagonal, is just going to be negative 2 times 3, negative 6, and so on. But then these are upper diagonal matrices, lower diagonal matrices, and diagonal matrices. Then the determinant of these matrices is just the product of the elements in the main diagonal. We're going to be using this. Now we're going to emphasize what happened with the determinant of a matrix when we do a row operation. Then let me just say how row operations change the determinant. And let me just say that if you have a matrix A here, and then you get a matrix B, Then if this is the determinant, we have the determinant of A here, and this is the determinant of B. Then if this B is obtained from this because you did something like changing two rows, then the determinant of B is equal to the negative the determinant of A. Now, if you get the B because you add to row J, you add alpha times row I, then the determinant of B is equal to the determinant of A. And finally, if you have A and you obtain B because you multiply by a non-zero number, let's say alpha times row I. If you multiply the row I by alpha with alpha non-zero, then the determinant of B is just alpha times the determinant of A. Then we're going to use this to compute the determinant of this matrix. Okay, let's start doing row operations. And let's suppose that this one we have the value for the determinant of this matrix is the determinant of A. Let's do some changes. Let's change row 2 by adding negative 3 times row 1, and let's change row 3 by adding negative 2 times row 1. When we do that change, we're going to place zeros in here. We get 1, negative 2, 3. Here negative 3 plus 3 is 0. Negative 3 times negative 2 is 6 plus 4 is 10. Negative 3 times 3 is negative 9 plus negative 2 is minus 11. Now negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times negative 2 is 4 plus 0 is 4. And negative 2 times 3 is negative 6 plus 4 is negative 2. Since these changes don't affect the determinant, then we have that the determinant of this matrix is also the determinant of A. These two matrices have the same determinant. But now let's multiply row 3 by 1/4. Then what do I get? I get 1, negative 2, 3, 0, 10, negative 11, 0, 1, negative 1/2. And what is the determinant of this matrix? Since I multiply row 3 by 1/4, the determinant of this matrix is 1/4 determinant of A. Now let's switch row 2 and row 3. When we switch these two rows, I get the matrix 1, negative 2, 3, 0, 1, negative 1/2, and 0, 10, negative 11. Then the determinant of this matrix is going to be the opposite of the determinant of this matrix. Then the determinant of this matrix is going to be negative 1/4 times the determinant of A. Finally, let me just do that operation here. Finally, if we change row 3 by adding negative 10 times row 2. If we do that change, then we will get 1, negative 2, 3, 0, 1, negative 1/2. And here I'm multiplying by negative 10 plus 10 is 0. And when I multiply by negative 10, I have 5. Negative 10 times 1/2 is positive 5 minus 11 is negative 6. And how is the determinant of these two matrices? We are doing this change, but this change doesn't change the determinant. That means that the determinant of this matrix is negative 1/4, the determinant of A. But then, what do we have at the end? We have that, let me just finish here. We have the negative 1/4, the determinant of A. We are looking for the determinant of A is equal to the determinant of this matrix. But this matrix is upper diagonal. Since this matrix is upper diagonal, we can easily compute the determinant of this matrix. And that determinant is 1 times negative 6, then it's negative 6. And then we can solve for the determinant of A. We just multiply by negative 4, and we get that the determinant of A is positive 24. Even though it doesn't look like it is a good system for this example, it turns out that this is one of the most efficient systems to compute the determinant of a matrix, especially when the matrix is a large matrix. Let's continue explaining the meaning of the determinant. If we have a matrix A, then we can think about the 3 rows. Let's suppose that we think about the vector B1 equal A, B, C, B2, D, E, F, and B3 equal to G, H, K. Then when we think about these 3 vectors, there are 3 vectors in the space. And we have the vector B1, B2, and B3. Then the determinant of A is a number. Then let's forget about if it is positive or negative, but then let's think about the absolute values of the determinant. This number, it represents the volume of the parallel pipe generated by B1, B2, and B3. Then these 3 vectors are 3 vectors in the space. Let's suppose that here we have B1, B2, and here we have B3. Then with these first 2 vectors, we can think about a parallelogram like this. This is a parallelogram. And then we just extend this parallelogram until you reach the tip of B3. And then you get the same parallelogram here. But then you connect these dots, right? And then this shape is a parallel pipe. And the volume of this is absolute value of the determinant. And let's see what happens if the determinant is positive. If the determinant of A is positive, that means that if you consider, if this is your vector 1 and this is your vector 2, then when you take your right hand and you place it in the vector 1 and you move toward the vector 2, then your thumb is pointing in one direction. If your vector 3 is pointing in the same direction as your thumb, then in this case the determinant is going to be positive. And if it is not pointing in that direction, then the determinant is going to be negative. For example, in this case, we have B1, B2. When we move from B1 to B2, then my thumb is pointing up, and this vector is like in the same direction. Then in this case, the determinant of this matrix, if this is the picture, this will have a determinant which is bigger than 0. If we have vectors like b1, b2, and b3, in this case, the parallel pipe would be like this, and then here you have this and this. This will be the parallel pipe. Then in this case, if you place your hand in the vector v1 and you move toward the vector v2, your right hand, when you use right hand, then your thumb is pointing up, but the vector 3 is pointing down. Therefore, in this case, the determinant of A is negative. This interpretation works if you use these vectors W1, the columns A, D, G, W2 equal to B, E, H, and W3 equal to C, F, K. Same thing, it doesn't matter if you use the 3 rows or the 3 columns. Notice that the order matters, and if you switch the order of 2, the determinant is going to change by a sign. Let me end up with another example. Then, if we want to use the Sarrus rule, then we need to add the 2 columns here, 1, 2, 3. We add the first column, and then we add the second column, and then we do these products, and then in this direction too. Let's see, when I multiply 1 times negative 5 is negative 5. I'm computing the determinant of A is negative 5. And here we have 2 times negative 1 is negative 2 times 3 is plus negative 6. Notice that those that comes in these directions are positive, and those that comes in this direction are negative. And then we have 3 times 2 times 0, it will be plus 0, minus, because it's coming in this direction, 3 times 1, 3 times 3 is 9, minus 1 times negative 1 times 0 is 0, and then minus 2 times 2 is 4, times negative 5 is negative 20. Then what do we get here? We get negative 11 minus 9 plus 20, and this is equal to 0. That means that this matrix, let me rewrite it, 1, 2, 3, 2, 1, negative 1, 3, 0, negative 5. The determinant of this matrix is 0. Let me use the Laplace expansion, and let me use the column 2. Then remember that the signs are positive, minus, positive, minus, positive, minus, positive, minus, positive. And then in this case, we start with this entry 2, but this one goes with a negative. Then the determinant of A is minus because of the position of this entry, and then minus, and then the entry 2 times the determinant of the matrix that you get when you remove this row and this column. 2, negative 1, 3, negative 5. 2, negative 1, 3, negative 5. And then we continue here, plus the value of the entry times the determinant that we get when we remove these two, this row and this column. 1, 3, 3, negative 5. 1, 3, 3, negative 5. And then plus 0 times the determinant of 1, 3, 2, negative 1. And then this is going to be negative 2 times, this is negative 10, minus negative 3, plus 1 times negative 5 minus 9, and then plus 0. Then we have negative 2 times, this is times negative 7, and then minus negative 5 minus 9 minus 14, and this is 14 minus 14, which is equal to 0. Let's practice the last technique that we learned to compute determinants, and is by using row reduction. Let's suppose that I want to use this one to put zeros in here. Let's start saying that the determinant of this matrix is what we want to find, and let's call it the determinant of A. And let's do these two changes. Row 2, I'm going to change it by adding negative 2 times row 1. And row 3, I'm going to change it by adding negative 3 times row 1. Then when I do that change, I get a new matrix. This row is going to stay the same, 1, 2, 3. And then here, when I multiply by negative 2 and add, I get 0. Multiply by negative 2 and add, I get negative 3. And if I multiply by negative 2 and add, negative 6 minus 1 is negative 7. Let's see what happened when I multiply by negative 3 and add that to row 3. Negative 3 and add, I get 0. Negative 3 times 2 is negative 6, plus 0 is negative 6. And negative 3 times 3 is negative 9, minus 5 is minus 14. Notice that if I ask myself what is the determinant of this new matrix, the determinant didn't change, because this type of row operations doesn't change the determinant. Now what I'm going to do is I'm going to change row 3 by adding negative 2 times row 2. I'm going to put a 0 here, and then what I get is 1, 2, 3, 0, negative 3, negative 7, and 0, 0, 0. An important property that I forgot to mention is that if a row of a matrix is the 0 vector, then its determinant is 0. Then in this case, this matrix has determinant equal to 0. Actually, we can see this also because this matrix is upper diagonal, and then the determinant is just the product of 1 times negative 3 times 0. Then, and what is the connection between the determinant of this matrix with the determinant of this matrix? Since I did this type of operation, then the determinant didn't change. That means that the determinant of A is equal to the determinant of this matrix, but the determinant of this matrix is 0. That means that we get that the determinant of A is also 0. We have this property too if we change a row by a column. If we have a matrix and we see that a column in that matrix is the 0 vector, then that matrix has determinant 0. What is the meaning of having a matrix with determinant 0? Let's erase this part. Again, let's suppose that we have A, B, C, D, E, F, G, H, K. Then we can consider the rows. B1 equal A, B, C. B2 equal to D, E, F. And B3 equal to G, H, K. If the determinant of A is equal to 0, then we can view that in several different ways. For example, one way is that the matrix A must be singular. Remember that means that the null of A is different from the vector 0, 0, 0 in this case. Their interpretation is that the vectors B1, B2, and B3 are linearly dependent. The other interpretation is that when you draw the vectors B1 and B2 and B3, all of these three vectors lies in a plane, or they may lie even in a line, but they don't span a parallel pipe. Finally, being linearly dependent, that means that one of the B sub i's is a linear combination of the others. We can't change the rows by the columns, and the same statements would be true. If we consider W1 equal A, D, G, W2 equal B, E, H, and W3 equal to C, F, K, then if the determinant of this matrix is 0, that means that these three vectors are linearly dependent, and it means that one of these vectors is a linear combination of the other two.